functor points. So for ring A, XA is the set of morphisms from spec of A to C. And in particular, if A is a field, right, then exactly what this corresponds to is a point X and then phi, a homomorphism from the residue field at X. So this is, take the stalk at X, mod out by the maximal ideal in the local ring. So this is a small k, not a big K, into A. So in particular, right, like if A were the rational numbers, the only way this could happen is if K of X is the rational numbers. Whereas if you have some field extension, you'll get, more field extensions that map into that. And like one sort of important point here is if I look at, for example, A1 of Q. So as you were just saying, the points of that, well, there's the generic point. And then the other points, it's sort of hard to draw because what's a point of this? It's a maximal ideal of Q adjoin T. So it's an irreducible monic polynomial over Q. So it's a point in, it's an algebraic, let's say, complex number, right? Somehow I don't really need to think of it in terms of complex numbers. I just need to think about the algebraic closure of Q, but one handy dandy way to think about that is to think about it inside C, up to the action of the Galois group. So every point in here corresponds to some orbit of the absolute Galois group of Q, and algebraic numbers. And then like this corresponds to some, so I have this is all kind of one point P, and KP is, Q adjoin T, mod that polynomial, right? And if this is Galois, right, then the different, let's call this A, right? I get different A points for all the different isomorphisms KP isomorphic to A. So that's where the Galois group shows up. That when I look at A points, I see the distinct points of this orbit as different A points. And right, we saw that with in the case of the real numbers, where you had the irreducible quadratic, and then when you looked at the C points, you had to choose an isomorphism of that quotient to C, which there are two of them that differ by complex conjugation. All right. So the other way we want to think about this is, as promised, we're supposed to think about functors. You can think about A maps to XA as a functor from the category of commutative rings to sets. And I want to emphasize here, right, I'm thinking about all commutative rings, and in many cases, there would be like none of these, right? So if I looked at A1 over Q and I tried to take its FP points, I should think carefully about whether I'm going to find any of those, but I'm pretty sure I'm not. No, because I'm not going to have any ring homomorphisms from the residue fields, which are all characteristic 0, into FP. right? So I can sort of see, oh, all my residue fields are characteristic 0 from the fact that I have no FP points for any P. Yes, I'm sorry, op, yes. Right. More generally, I can think about points for non-affine schemes. So I could think about XZ as the morphisms in the category of schemes from Z to X. Just spec of a ring is the most common situation where you would do this. So I can think of that as a functor from schemes to sets. Okay. It's basically the Yoneda lemma tells me that the functor from schemes to sets uniquely characterizes X. So again, you could actually define schemes by defining what these functors are. That sounds slightly circular because I have the category of schemes here, but you can check, actually, I only need affine schemes. So I only need the functor from C ring to set. And the reason is that every scheme has an open affine cover. And I can describe the intersections between open affines using affines. So if you want to be fancy, because I can write every scheme as a co-limit of a map between affine schemes, tells me I only need to know about that part of the category. Yes. Yes, it does. Right, because I mean, think about what would happen if I had two schemes which gave me the same functor here. I would look at an open cover of one of them, and those for the affine sets in my open cover, I get points in here. I look at the same points for the other guy, and I see that that's an open cover of the other guy, which glues together the same. Yes. I mean, right, this characterizes X uniquely up to unique isomorphism, right? So an isomorphism of these functors is the same thing as an isomorphism of schemes. And similarly here, even if you only think about commutative rings. So I mean, you can think about this concretely in terms of, oh, I applied this functor to the open sets and then to affines that cover the intersections of the opens. But I'm just saying, like, oh, it's because any scheme is a co-limit of a diagram of affine schemes. I'm ignoring size issues. I I'm not going to say the word Grothendieck universe again. That's something you can read on your own. So I mean, the short answer is people have worried about this, but I'm not one of those people, and I'm not going to try to make you guys be one of those people. That's your decision. Okay. So what are some more examples of morphisms? So, we know about maps between affine schemes. What about projective schemes? So imagine that I have two graded rings, R and S, and I have a graded ring homomorphism from R to S. Okay, you might hope that this gives you a morphism between the projects, but you have to be a tiny bit careful. So what's true here, right, is if I take some element F and R, I can look at phi of F. And I get a map between the localizations. So I get an induced map from RF to S of phi of F. Okay, so far so good. If I take spec, well, this becomes df. If I take spec of degree 0 part, should emphasize that, spec of degree 0. And if I take spec of degree 0 part here, I got phi of f. And I get a map this way. I should have made these kind of squigglier arrows because this is a map. I'm doing an operation. Okay, and it's not too hard to check that those are compatible on overlaps. So it's looking pretty good for gluing these together into a morphism. But there's a problem, which is what if proj of S isn't covered by open subsets of this form? So I'm going to possibly have some points that never sit inside here. And so I never get my map to be defined on them. And the fancy way to say this is that I look at, here I take proj of S, and what is the stuff which is never in one of these sets? It's all the ideals which contain the image of the irrelevant ideal in R. So the thing I have to pull out is the vanishing set of the image of the irrelevant ideal. So exactly the problem here is, right, that the pre-image of a prime ideal is a prime ideal, and the pre-image of a homogeneous prime ideal is a homogeneous prime ideal, because this is a map of graded rings. But I also have this condition that I'm not supposed to contain the irrelevant ideal. And that might not be preserved under pullback. So these are exactly the prime ideals in S that don't contain the irrelevant ideal in S, but their pre-image in R does. So I get a morphism from proj of S minus this open subset to proj of R. Sorry, what? Yeah, yes, I'm sorry. That's. Yeah, sorry. I should have had it slashed the other way, but I did a bad job. All right, cool. Yeah, I think I drew it wrong in my notes. Okay. So, for example, if I look at K adjoin x1 up through xn, right, and then K adjoin one fewer variable, then I have obvious maps both directions. I have a map that sets xn to 0, and I have a map that's just the obvious inclusion. All right, so if I do the first of those, setting xn to 0, well, here I have pn. Now, let me start at x0, like you usually want to with projective space. So here I have pn minus 1. This first map gives me a map this way, pn minus 1 into pn. And what is this? I just look at what happens to functions, right? So it has to be that pulling back whatever these guys are that aren't quite functions under this map corresponds to this ring homomorphism. So this is the map that takes a point x0 up to xn minus 1. And I know that not all points of projective space actually have that form, but bear with me. And sends it to this guy. Right? Just tack a 0 onto the end. And that's a perfectly well-defined morphism. And the reason for that is if I take the pre-image of the irrelevant ideal here, I get the irrelevant ideal. Or sorry, no, if I look at the irrelevant ideal here and I look at the ideal that its image generates, that's the irrelevant ideal. On the other hand, the map this way, well, I still have the same spaces, and I'm trying to define a map back this way. And if I think about the same principle, what this map is trying to do is take x0 up through xn and map it to x0 up through xn minus 1. But there's an obvious problem with this map, right? This map can take a point where all the coordinates except the nth one are 0, and it can send it to a point where all the coordinates are 0. So I'd say that's because if I take the irrelevant ideal here and look at its image here, I get the ideal that vanishes at that one point. So I don't get a map from Pn minus 1. I get a map from Pn minus 1 minus this single point. Yeah. So sorry. So map from here to here. Certainly, this is a proper subscheme. We haven't talked about closed subschemes, but I'm going to miss some points. In fact, I'm going to miss most of the points. Yeah. Oh, yes. The map is defined everywhere. And you can see that from the formula, but it also sort of follows from this algebra. Right? And it's because if I take the irrelevant ideal here, its image generates the irrelevant ideal here. Whereas the other way around, it's not true. This is the vanishing set of the image of the irrelevant ideal. And polynomials one guy lower. Okay. So a few things to say about this. One thing to say is, so for affine schemes, the morphisms between them are just morphisms between the corresponding rings. Active schemes, you have to be a lot more careful about this. And basically the reason is when you write something as an affine scheme, you've written it uniquely. The ring that you've written it as spec of is canonical. You don't have any choice about it. It's the sections of the structure sheaf on the variety. Whereas when you write something as a proj, it's not unique. So for example, first let me state the theorem. And we'll sort of see other versions of this theorem later. If f from proj of S to proj of R is a morphism of schemes, then there exists S prime such that proj of S is isomorphic to proj of S prime. A homomorphism Oh, we are hearing them breaking the concrete. Okay. I've been claiming that it wasn't affecting this part of the building, but apparently I was wrong. All right. Um, so there exists a homomorphism from R to S prime that induces this map of schemes. So we'll see more interesting manifestations of this later. Um, the sort of, for those of you who know about line bundles, this has to do with when you write something as proj of a ring, you're not just writing it as a projective variety, you're writing it, not just writing it as a scheme, you're writing it as a scheme with a choice of ample line bundle. And it's even less unique than that, but that's sort of the really important thing, is that there are different ample line bundles. And so this S prime comes from choosing a potentially different ample line bundle in proj of S. All right, if you don't know those words, don't worry about it. We'll cover it later. Um, so uh, like one very obvious sort of dumb example of this is if I take my R, I can then look at the d-upal version of it, which means I look at the graded ring, which is only the graded pieces whose degrees are divisible by R. R, D, N. And it is a matter of personal taste, whether you call this the degree N stuff or the degree DN stuff, you'll get the same answer no matter what. That's another sort of stupid redundancy. Um, so you can easily check that proj of R, when I do this multiplying by D thing, is the same as proj of R of dot. The point just being that if I ever want to look at D plus of F here, well, here I could just look at D plus of F to the D. And those are isomorphic. So I don't get anything different if I only look at the open subsets that come from inverting Dth powers of things. No, that's a dot. So the point is just forgetting about the terms whose degrees aren't divisible by D doesn't change anything for what proj is. So somehow like this is one example of the kind of non-uniqueness of proj. You could do other dumb stuff. You can delete any finite number, delete the degrees from 1 up through k for any k, and you won't change what proj is for exactly the same reason. Because taking higher power things doesn't, this doesn't change what the degree 0 part of the localization of this ring is. I just have to take higher powers of things. So one thing that comes up with projective space is you might take all polynomials, and then you might take just this grading only divisible by D guys, right? And then the degree 1 things in here would be given by the degree N monomials the degree D monomials in N things. So I have a map here from A of Y, where A is the indexing for monomials of degree D. So this is what's called the Veronese embedding, right? There's a corresponding map from the projective space, oh, I should have put 0 here, sorry, in n variables into the projective space. Here I want n plus 1, choose d minus 1, I think, called the Veronese embedding or the duple embedding. Sorry, it's n. Oh, sorry. Yes, it's you're right. Stars and bars. Yeah, probably. Sorry, I didn't double check this before. However many of these there are, it's some binomial coefficient. Um, or duple. All right, and this is sort of useful because this actually lets us replace proj of a random graded ring with proj, which is actually generated in degree 1. So if you take d sufficiently large, there's an argument in Buckhill or he kind of gives you hints for how to do the argument to show that you can just assume that all the generators are in degree 1. Here, because the number of variables is some binomial coefficient, and then I take the projective space, and I get the number of variables minus 1. So, for example, if n equals 2 and d equals 2, there are 3 variables, and I get a map from P1 into P2, which is the twisted cubic. Right. Yeah. Right. This sends x0, x1 to x0 squared, x0, x1, x1 squared. This is a point in P2. That's where the minus 1 comes from. All right. Well, whatever. It doesn't matter. Whatever. Maybe there's I kind of think there's a plus 1 here because this guy has n plus 1 variables. Okay, cool. Are there any questions? And note this again has this property that I get a map on the whole space because the image of the irrelevant ideal here generates the irrelevant ideal here. So kind of most often what will happen is you will have graded rings that are all generated in degree 1, and you'll have a map in degree 1. And most often, if that map is surjective, the map is defined everywhere. If it's not surjective, then you should be pretty worried. All right. So another thing this brings up is, well, suddenly if I start looking at all my graded ring maps, I get a lot of maps which aren't defined on the whole thing, they're just defined on an open subset. And that's sort of a notion that comes up often enough that it gets its own name. Those are called rational maps. You could also call them rational morphisms. So this is by analogy with rational functions. So for simplicity, I'm going to let x and y be reduced. I'm just following Vakiel here. The point is mainly that there isn't 100% consensus about what the correct definition of rational map is if x and y aren't reduced. So we would kind of go down a long rabbit hole that isn't that important for us. So a rational map so we write this as X, and then a dashed arrow, and then Y. And this is to tell us, and I could also say rational morphism. Certainly my habit and many other people's habits is to just say map, and you understand that that means a morphism in the relevant category. So when I say a map between schemes, I mean a morphism of schemes. All right. Is a map from U of X a dense open set into Y? So phi is an actual map from an open subset of X into Y. And there's an important proviso here, which is that this open subset isn't canonical. I have to consider these modulo an equivalence relation. Mod pi on U is equivalent to pi prime on V if there exists W in the intersection of U and V still dense, such that these guys agree. So if you want to, you can recognize this as a filtered covalent. Yeah. Yeah. Yes. No, it's the equivalent. So you can think of it as a colimit, right? It's like a stalk, right? An element of a stalk isn't a section on any particular open subset, but it always has a representative of one. So similarly here, this guy isn't defined on specifically any one open subset, but I can always pick a representative of it, which is defined on some open subset. All right, and a particularly important condition is we call these dominant if the image is dense. So this is an actual honest morphism, which isn't dominant. This is a rational morphism, which is dominant. So the image, right, what do I mean by the image? I mean the image of U, and you can check that if two things are equivalent under this relation and one of them has dense image, the other one has dense image. Right, it's key that my U is always dense, right? So I could have like multiple components, and if I allowed myself to restrict to an open that was only in one of them, I could mess up this condition. But because I'm requiring dense, right? I mean, somehow one way to say this is that the generic point of every component is in the image, right? And that's not going to change restricting to a smaller open subset, because I always have, right? Being dense exactly means I get the generic points of all the components. So I just look at where those go. No, no. There are lots of birational maps between irreducible things which aren't isomorphisms. Yes. Oh, you just mean that I don't need to require dense. Yes. If X is irreducible, then requiring dense here is redundant. Now, it's not true that if y is irreducible, you're automatically dominant because you can have lower dimension. Yes, you're right that most often my x will be irreducible, and so it won't matter whether I say dense or not. But right, this is an example where both things are irreducible, but this is not dominant because its image isn't dense. Its image is a proper closed subset. All right, so I think probably the most important of these things is it gets us back to these questions about fields. So if I have x goes to y, for indeed x and y are, well, I might as well just assume they're integral, right? Because I already assumed they were reduced. So if I assume they're irreducible, that means they're integral. And pi dominant, well, that means that here I have a generic point a to x. Here I have a generic point a to y. Those are going to be in every open subset. So my dominant rational map maps this generic point to this generic point. And I have a pullback map on the stalks. So if I take the local ring of y at a to y, which is the fraction field of the variety, or I think people usually call it the function field of the variety. It's, as you saw in your homework, it's the fraction field of the sections on any affine open in y. That maps to the same thing for x. These are the function fields. And note here, I really, really need that my map is dominant, right? If you looked here and tried to construct a map between the fraction fields, it wouldn't work out because there would be polynomials that get mapped to 0, right? So the key property of being dominant is you can't have a non-zero function pull it back and get 0. Because that would prove it was 0 on a dense open subset. All right. So the cool thing is this is kind of reversible. You should think of rational maps between integral varieties as being almost the same thing as maps between their function fields. Yeah. Yeah. I mean, you have to be a little bit careful, but I'm assuming that I'm integral. I think you might actually run into trouble if, right, not Hausdorff, but separated might be the relevant thing here. But on an integral thing, the sections on any open subset inject into the sections on the generic pointer. That's sort of why you have a well-defined function field. So the section on an integral thing, the sections on any open subset are a subring of this function field. All right, so to get a kind of converse, to get a map, a rational map, starting from a map of fields, I need a few more hypotheses. So if X and Y are finite type, over a ring K, maybe I won't use K, I have too many Ks running around, over A. So I have some base ring A, and X and Y are finite type over A. So locally, they're spec of finitely generated A algebras. And phi an amorphism. So I'll just remind you, by that I mean being finite type over A means I have a structure map to spec of A. A pullback of functions on spec of A gives me a map of A into the section, so I'm in the open set. I also have that for Y, and I'm asking that I have a map between X and Y where this diagram commutes, which just says that when I pull back functions on here, it sends the functions that come from A here to the functions that come from A here. So the pullback map is a map of A algebras. I'll even say that. So if I look at, right, I want to look at O of Y of U, that maps into O of X of phi inverse of U. Should be a map of A algebras. So this is what I mean by like being a scheme over spec A is the scheme version of being an A algebra. Sort of the scheme analog of that. All right. Then any homomorphism I should say a homomorphism from K of Y to K of X arises from a unique rational map. Okay, cool. So since I'm only trying to construct a rational map, it won't change anything if I replace A and B, X and Y, by affine open subsets. So, and assume that X is spec of R and Y is spec of S, and that these are finitely generated A algebras. So that means that R is take A, join some X's, mod out by an ideal, and S is join some Y's, and mod out by an ideal. Because the original schemes I started with are integral, these are going to be domains. So if I have a homomorphism from K of Y to K of X, well, S is a subring of K of Y. Right? K of Y is actually the fraction field of S. So I get, didn't give this a name, P mapping from S into the fraction field of R, which is K of X. And this, I'm thinking of this as a subring of K of Y. Okay, so what does the finiteness let me do? The finiteness is actually pretty important here. This means if I look at phi of yi, I get some fraction ai over di. And, well, this isn't necessarily elements of R. There's nothing special about R. Wouldn't change anything if I replaced R by a localization by a single element, right? I want to preserve being finitely generated. So I shouldn't do something like localize at a prime ideal, but localizing at one element is fine. So if I replace R by R prime, which is R, and now I localize the product of all these Ds. Right? So the finite typeness was important because I only need to invert finitely many denominators. Right? If I had infinitely many denominators, I would be host, but I only have finitely, so I'm okay. So I get D from S to R prime. And so a map back the other way from spec of R prime, which is an open subset of X, into spec of S, which is an open subset of Y. And this is the rational map I was looking for. Yeah. I didn't say that. I don't think you should do that. I wouldn't conclude that you can do that. Oh, sure, fine. Yes, you can do that if you want to. It doesn't change anything. Right? The number of variables didn't make it play any role here, but it's very important there were finitely many. All right. So rational maps are basically field extensions. You have to be careful about this. You do need the finite generation. So note, there does not exist a rational map from like spec Z to spec Q, even though they have the same fraction field. Right? The problem is an open subset of spec Z is only going to invert finitely many primes. And to get a map from here to here, I need to invert all the primes. Right? Somehow I'm trying to construct a map from Q to Z. Well, that definitely doesn't work. Now, a rational map would mean constructing a map into Z adjoin the inverse of one number, because every open subset has that form. And I still can't do this, right? There will be situations where being able to invert some n will let you construct a map that you didn't have before, and that would be a rational map. So there is a rational map from spec Z to spec Z invert 1 over n, which is just kind of the inverse of the map of schemes this way. Right. This is, I take spec of Z and then I remove all the primes that divide n. Right. So this sort of makes more precise this idea I was saying about like field extensions you can sort of think of as like covers. So we haven't gotten to this yet, but if I have a finite field extension, I can arrange this so that R prime is a finitely generated module over S. And so then I'll have like, I'll have some bad locus, and then over the good locus, I'll have a nice covering. If I'm willing to keep passing to smaller open subsets. Yeah, I mean that's one way to think about it. Yeah, I mean, sort of once you've gotten to that point, then like, right. Well, we just explaining this requires like lots of concepts we haven't used yet, so I wouldn't worry about it. But it's sort of um, the locus where it stops being a cover has to become non-reduced because some of the points need to collide. And that's exactly what ramification is. All right, probably seriously out of time. Oh yeah, I'm seriously out of time. All right, no, that's as far as we got. So we'll talk more next time.